So, what we have is I think 3 flap, 2 lag, 1 torsion, 1 axial. So, about R3 or yeah 3, 2, 1, 1, 3, 2, 1, 1, but 6 or 7, 8 modes or 9 modes we take, or 4 flap, 2, 3 lag, torsion, then we do system. Okay. See, we all learnt very simple equation, first order equation. If you take x dot equals Ax, A is a constant. This you write immediately the solution as x is equal to some constant e to the power what, right, x of t. This is the solution. That constant is the initial condition, maybe at t equal to 0, x is equal to x naught. So, you may write this as basically x naught e to the power a t. That means this particular term, as time evolves from 0, is changing the initial condition, in the sense not that initial condition is changed, initial condition is getting multiplied to some time varying function, gives you the response at any specific time. Similarly, let us now go to this equation. Okay. Now, how will I write my solution? A of t can be, it is still a linear system, it can be any time varying function. Now, if you assume this solution x of t as e to the power integral t0 to t a tau d tau and then x0, x0 is the initial condition. This is the solution. This is the solution to this equation, because if you differentiate this, what will happen? X dot e to the power, so that will stay as it is. So, e to the power minus t0 t a tau d tau. Then you differentiate this part, that will be nothing but a t and x naught. Okay. And since this term, okay, what? This is x t. So, you will find a of t x. So, you say this is my solution, all right. Okay. Now, you just say similar, I said this is x naught is the initial condition and there is a time varying function which is getting multiplied to initial condition to give you response at any particular time, and this is called state transition if it is a matrix, it is a matrix problem. Here it is just only function, okay. And this state transition phi is e to the power integral some t0 to t a of tau d tau. Okay. Now, one key difference between this and that, here this is also you can write if a is a constant, okay. if A is a constant, what will happen? This will come out, you will have T minus T naught, but T minus T naught is one term. Okay. That means the difference between the initial and the response at any time. Okay. So, if it is a constant thing, you will find the response is only the difference between the time, whereas if A is a general time function, you will find T naught as well as T, but it will not be the difference. It need not be the difference. It is a function of both T and T naught. It is not the difference between the initial and final time that is determining the response. Okay, this is the character, and this is called the state transition in a matrix form, because we do not solve this problem. Matrix is called a state transition matrix. First order, one variable you can solve. Now you extend it to matrix equation. That is the starting point. Why we have to go for matrix formulation is, I am writing now, you take it x dot is A x. Okay. This you all, if A is a, this is a, please note, this can be n by 1. Okay. This you must have studied. Okay. You do not actually, this is called the state space representation or a first order representation. This is basically called state space. Because if you are given a ODE, linear, all we are talking linear. If you are given an ordinary differential equation of any order, please understand, it can be second order, it can be third order, it can be nth order. You can convert that into this format always. I will just do that a little bit so that you know that. Suppose you take the simple equation, you are all familiar with the second order differential equation. Mx double dot kx is let us take it 0, f of t means, otherwise that will be a forcing function. Now this is a second order equation, I can have third order also. How will I write in this form? Okay, this is what the state space representation is. Okay. What you do is, there is a very clear simple thing, you call this as x1, you call this as x2. Okay. Now your equation x1 x2 dot time derivative, that is x1 dot x2 dot. X1 dot is what? X1 dot is basically, x1 is x, x dot is x2. So x1 dot is x2. Okay. Now x2 dot is nothing but x double dot, because x2 dot, okay, but x2 is x dot, therefore that is nothing but x double dot. So you can best is you take this equation minus Cx dot minus Kx, right. You know this is x1, this is x2, this is x2 dot. Okay. So you will have minus this is x2, this is k by m minus c over m, that is all. This is the state space form, because what we have done is y state is, in this case we are talking about position is a state, velocity is another state. If I know position and velocity, then I know the other derivative, because if I know x and x dot, I know x double dot. It is not that I have to solve separately for that, you understand, but I must know x and x dot. Is it clear? And now you see this can be converted into matrix form also. What you do is, instead of single values, you may have mx double dot. These are all matrix. Now how will you get the form is, you will put like this x1 x2, because this is again a vector. So you will put dot, you will put 0 1, and here you put minus m inverse k minus m inverse c, and you will put x1 x2, that is all. This is a matrix, okay. Is it clear? So what we have converted is, what is the one second order differential equation is converted into two first order differential equations, but they are coupled, okay. It is not that they are independent, not like that form, okay. So one second order you convert to two first order coupled. If there are third order equation, you can convert to three first order equation, okay. Why all this is done is, because then you have only one solution technique, that is it. You solve only this problem. If you know the solution technique for this problem, every problem can be handled, you understand, in the ODE. That is why you learn, now you will be able to relate why you learn matrix algebra, okay. See, these are very, see, initially when it is taught, each is taught independently. Then you say, oh, I am able to relate various things, because if I know, because we are going to have in the aerospace field at least our stability problems, vibration problems, load, anything, rotor blade, all problems will come under that. You will try to put it in this type of format, and then immediately convert to this format to get the solution, okay. Now you know how to get the state space form. That is why if you are given a differential equation, you should be able to convert to state space form. So this is a standard, that is all. You take this, take the other term, put a m inverse, this goes to m inverse k, m inverse c straight, okay. Now we will go and then solve this problem, because the solution, if A is a constant matrix, okay, that is x dot is, if A is constant, then you will say solution can be x naught, this is a vector, or in other words you may write it in this fashion, e to the power a t x 0, okay. E to the power a, please understand, this is a matrix. You can put it, if you want, you can put it like this. It is not that every element is exponentially increased, please understand. This you can expand like I plus but Euler expansion, okay, 1 by 2, I think 2 factorial, what, a square, right, like that it goes, okay. This is the expansion. Now if I differentiate into, you will put okay, this is x 0, okay. I differentiate this, what will happen? This will be 0, this will be A. Okay. So, if I put x dot, this is 0, this will become A plus A what square t plus A cube t square over 2, like that it will go, right, into anyway x naught will be there. You take out the A, right. When you take out A, then what is left is A, this is, this term will be there, okay. Because if you take A outside this side, this is nothing but 1 plus A t plus the whole thing, which is nothing but the, so you will have A e to the power A t x naught. This is nothing but A x, okay. So, x dot is A x. Now, this is, that is why you are doing all these things is, slowly you will realize, you can, you first thing is you are learnt about diagonalization of a matrix, real matrix. So, you have the similarity transformation, okay. You get the eigenvalues, eigenvectors, you pre-multiply and then do, okay. Because when you do that, if this matrix, you can convert it like that, you know that U inverse, what I think I will put it, A is Q inverse lambda Q, something like that, similarity transformation, right, yes or no, somewhere you have learnt, huh? Yes, okay. This is what, now if you substitute this here, what will happen is this will become, you can take out Q, the inside one will be nothing but e to the power lambda t, that is the eigenvalue. So, you really know whether the system is stable or unstable or anything like that, because A square is what, A into A into A, what Q inverse will go off, you will get lambda square, okay. So, you will have a Q inverse. So, I will write it, maybe that will become, see, you substitute this here, then what will happen, x becomes I plus A is Q inverse lambda Q t plus 1 by 2 factorial Q inverse lambda square Q, because in between Q inverse Q they will become identity, okay, because A square is what, A. You substitute this and like that this will go on and you will have x naught. What you do is you can write this as Q inverse Q. So, this can come as Q inverse 1 plus or I, you can take it, lambda plus lambda square over into Q x naught, okay. This is what? So, Q inverse e to the power lambda t Q x naught, you follow. Now, you see it is a very interesting thing. The eigenvector, please remember, the eigenvectors of the matrix A is the same as the eigenvector of matrix this, e to the power at is a matrix. Only thing is you don't know how to evaluate, that is all, because it is a series, right. The eigenvector of this matrix e to the power at is same as the eigenvector of A, but eigenvalues are not same, okay, because this is eigenvalue is lambda, for this that eigenvalue is this e to the power lambda t. Now, you basically what you do for this kind of problems, if you are given, you want to analyze stability, because all flight mechanics problems, everything you analyze stability. You want to know whether the system is stable or not. You look at straight away, go solve the eigenvalues of this problem. Okay. Once you know the eigenvalue, it will be a complex, because we are not dealing with real, symmetric, positive, definite, nothing of that sort, because you see this is not the symmetric matrix first of all. Of course, this is a real matrix, this is not symmetric. So, eigenvalues can be real, complex, anything. So, there is no specific condition, you understand. So, you get the roots, and those roots essentially tell you how the system is stable or not, and if it is stable, how much stable, or if it is unstable, how far it is unstable in the root locus. Now, you know that why root locus is used, and then you want to change the system, because now you say I go change my system A, so that make it stable. Sometimes you cannot make it stable. Okay. Then you start feedback control. This is how the whole thing starts, the entire subject of, then you can have a external loading. Then the control system, if you go, they will put x dot equals Ax plus B u. Now, for helicopters, u is theta naught, theta 1c, theta 1s, theta tail rotor. So, u is the control angle, pilot gives. Then this. Now, you say you want to stabilize, automatic stabilization, that means you have to go give a feedback based on how the system is measured. That we will leave it, we will not bother about the feedback control and other things. Just basic system, this is the system. Is the system inherently stable or unstable is determined purely by the matrix A. Okay. Here we look for the eigenvalue. Eigenvalues will have complex roots, real part, imaginary part. So, you say your lambda some kth root sigma k plus minus I omega k. If sigma k is positive, then you say e to the power positive, positive is it will grow with time. So, it is unstable. If sigma is negative, it is stable, but this omega will make it oscillatory, whether it is a oscillatory mode or it is a non-oscillatory mode. Some modes can be oscillatory, some modes need not be oscillatory, you can have only real roots, so that means this will not be there. Okay. So, this is what you analyze. Now, the question is, if A is not constant, because for our, if you take the flap equation itself, it is a time varying. Okay. Just the flap equation, because you can write flap equation in that format, that state space form. The moment you put it in state space form, you will have sin psi, cos psi, which basically that is omega t, time varying. So, your matrix system, this is time varying. If it is time varying, how will I solve? Okay, is the question. Now, time varying arbitrarily is one, another one periodically time varying, in the sense A repeats itself, in the flap motion it repeats. Now, that is slightly, I do not think we will have time to do that part, but that is very interesting. How do you, that is the Floquet theory. Now, we will only discuss, I will just briefly say, if A is a function of time, how do we get the solution? Any arbitrary function of time. Okay. So, I will erase this whole thing and we will say this is the A of t. Now, we can only write the solution. This is a matrix, maybe n by 1, n cross n and n cross 1. I am writing the solution because we said the initial state is getting changed, that is all. So, I put that all. This is the initial, T naught is the initial condition, phi t is the state transition matrix. Okay. This is a n by n non singular, okay, matrix, but what does it satisfy? It satisfies phi dot t comma t 0 is A of t phi t comma t 0. This has to satisfy this condition, satisfying the condition. Okay, you can put it. This is the condition, please note. Phi dot, this looks like this equation itself, but here these are all states. This is the state transition matrix. So, you may call this as a state transition. Okay. Now, you can verify why it has to be. Okay. That is, we know that this condition, right. The first thing is, if you set t equals t naught, that means this is x t naught, x t naught equal to phi t naught t naught, that means phi t naught must be I, this is I, okay, first condition. So, you know here phi t naught is I, okay. Next, you take a derivative of this equation, because we will give a proof that it has to be like this. If you give a proof, x dot t is what? D over dt of phi t comma t naught x t naught, which is phi dot t comma t naught x naught, sorry, x t naught, okay, which is also, this is what? This is nothing but our original equation A of t x. This is what this equation is. Now, what is x? X is A t this. So, phi t comma t naught x t naught. So, you see okay. So, you see this is equal to this, because either that or you substitute now in this, you can substitute this. This is what? A t phi t t 0. So, phi t comma t 0 x t 0. So, you see x dot t is this, x dot t is this, okay, which means both are same. Therefore, the characteristic of that state transition matrix is it must satisfy this condition, and phi T0 T0 is I. Okay, now we set the condition, but how do we get it? Okay, there is no easy way to get it. You can't write it as a matrix exponential. Why we cannot write it as a matrix? Like we wrote e power a t. In the single case, we put integral t1 to some t0 to t a of tau d tau. Can we do the same thing here? You can do, provided I will show some condition is satisfied, otherwise you cannot do. Is it clear? I will erase this part. Okay. So, you have given the proof that phi dot, what is the condition for the transition matrix? It must satisfy this with this, that is all. Now, can we write phi as a matrix exponential? That is, I am going to put, because you said this is the equation phi t t naught, I am going to write can we write, okay, e to the power because what was our equation? Our equation is phi t t naught dot equals a t phi t t naught. Can we write in this fashion? You can write provided okay, that a of t and integral commute, please note, provided a t and this commute. Commute means this times this is equal to that times this, a b equal to b a. Only if they commute, otherwise you cannot do it, but it is possible only when a is constant or if a is diagonal, otherwise you cannot do it. Okay. For a general case, you will not say a b equal to b a. Please note that in the matrix 2 into 3 one number, yes, 2 3 is 3 2, that is 6, this is 6, but you cannot put it for matrices. Okay. So, these are all very important, that is why as an operation is it commuting. So, provided it commutes, you can write the solution. Suppose if they do not commute, sorry, this is not the solution. Okay. Then how do you say that they have to commute? That is purely from this proof is here. I will give the proof. That is, you do the expansion, that is e to the power, this is a matrix only. So, you can expand it I plus integral t0 to t a of tau d tau plus 2 factorial, you will have 2 t0 t a tau d tau a tau d tau plus so on. Okay. Now, you see this is this expansion. Now, if I differentiate phi dot, this is a t, okay, but this will be 1 by 2 factorial a of t integral t0 t a tau d tau plus 1 by 2 factorial integral t0 t a tau d tau and then a t, because this, okay, first you take this, take. Now, if these two commuting, then this is, you can take out a outside. Okay. If they do not, you can write this solution. You follow? Now, this is the main problem. In if they do not commute, how will you write the solution? If they commute, you can put it in this format. So, do not commute, I will write the solution. It is no way you can do by hand, it is a, you have to numerically calculate, or some simple problem you can integrate and then show. So, what I will do is I will show that part. If they do not commute, the general solution. Okay. This is again a series. So, general solution is, this is a series expansion I plus integral T0 to T A of tau d tau plus I will put tau 1, okay. A tau 1, I open a bracket here, here I put one more T0 to tau 1 A tau 2 d tau 2 close, put d tau 1. Okay. Please note, this is a integration inside you do, and if you want to go to the third term, it will be still T0 to T A tau 1, you open a bracket T0 to tau 1 A tau 2, okay. Open one more bracket, put integral T0 tau 2 A tau 3 d tau 3 close, d tau 2, then close d tau 1, okay, plus so on, so on, so on. Okay. This you can show, because what you do when I differentiate this phi dot, this is 0, this is AT. Here what will happen, because the entire thing is over T. So, tau 1, this will become AT and this will stay as it is, because this is just a dummy index. Okay. Like that, what will happen is one by one it will stay as it is, and this is the series solution. You have to do numerically only, you cannot, there is no way you can compute this easily. Okay. This is as far as a general AFT is concerned. Now, I will give one small example I will solve. After that we will, I will just briefly mention, but we will not be able to do it because that derivation takes a lot of time, that proof, okay. But that is an interesting thing. Suppose you take a simple problem, dot 0 1 0 t. Now, you try to get the equation by yourself, okay. With the T0 as 0, compute transition matrix. Transition matrix, basically what is the solution to this problem. So, you solve phi t comma T0. So, what it will have, very first is I is as it is, okay. Then the second term will come A tau d tau, you have to put that, that means 0 1 0 t, put the integral, that will become 0 tau. So, this will become first term, that is integral 0 to t a tau d tau is nothing but 0 to t 0 1 0 tau d tau, which is okay. That is the first part, first term. This is the first term. Now you have to go to the second term. So this is I, maybe I will write it, this is 1 0 0 1 and this term is 0 t 0 t square over 2, then plus we have to calculate this term. That will be, because we can use tau, maybe I will do it, that term will be 0 to first you evaluate tau 1. Okay. Now this will be so you are going to have, this is tau 1 square over 2. Okay. This you multiply to, now you have to do this 0 to t a tau 1, a tau 1 will be 0 1 0 tau 1 multiplied to 0 tau 1 0 tau 1 square over 2 d tau 1. Okay. Because this you put, then you multiply. When you do that, then you take that matrix multiplication. Okay. This will become what? Integral 0 to t, I think 0 0, I think tau 1 square over 2 and then tau 1 cube over 2. Okay. D tau 1. Okay. Now this again 0 0, this is tau 1 cube by 6 and the limit, this is tau 1 4 by 8. So that will be t. So the third term will become like this, 0 t cube over 6 0 t 4 over 8 plus so on and so forth, because I am not, this is what the general solution is. Now you add all of them, that is your solution. So 1, this term will be 1, here you will have t cube by 6 etc. Here you will have 1 plus t square over 2 plus t 4 over 8 etc. it will go. So like that you will have a long series. Okay. This you have to do only numerical. Now the next question comes, okay, you wrote a very general AT. I am not interested in AT, I am interested in AT which is periodic. Okay. But there are a very special equation, this you maybe, I do not know whether you are exposed to or not. There is something called a Matthew equation. Okay. Matthew, it is by, I will just write that equation, this is just for your this is Matthew equation. This is one, or you can write it in another form also. There are various types of ways it can be written. Another way is they write d square f by dt square, sorry dx square lambda minus h square cos 2x f is 0. Any form, any all are pretty much same. Okay. This is called Matthew equation. Here it is periodic. Okay, but of course this is a second order. You have to convert to first order. You can do what initially people were interested in seeing for what combination of lambda and h square, okay, combination the solution is stable. Okay. So, if you look at some advanced books, they call it some C function, S function, something like that. Okay. Though whether they will give the condition of stable condition, that means at this, for this combination of values I will get a stable means a periodic solution, and there is a diagram, I cannot draw the diagram, the region of stability, for what combinations it will be stable, for what combination the system is unstable. But it will not tell you what is the value of damping. Okay. You can only say it is stable, it is unstable. Now you may ask how stable it is, am I near the imaginary axis, how close I am. See, if you are very far on either side you are highly stable, but if you are very near, your stability is just the marginal stable, but that result will not give you that. Okay. But it will tell you the regions, that is a separate formulation derivation. You assume a series solution and then put the condition that it is stable, then what should be the values. Okay. There are various, the period of the solution can be t or t by 2, various type of sine function, cos function, all those things are there. I leave out that part. The Floquet theory says if x dot is a of t xt and a of t plus t is a of t, periodic, because we are interested in periodic solution. Okay. If I will not give the proof, because proof I have, I will simply mention this statement. If you have this condition, what is the form of, please understand, my transition matrix? Not table, form. This is my equation which is periodic, please understand. It is a time varying equation only. Only thing is time varying rather than very general. Very general I wrote the long, what is that series solution. Okay. If a of t is periodic, the Floquet theory, this is what Floquet, we call it Floquet-Lyapunov theorem, Floquet theorem, anything you can call, Lyapunov. Okay. You may find it in different form, but I have got it from some notes, I am keeping this way. What it says is the form of this, there is a proof I have, it will be in this form. And P of t is P of t plus t. The form of the transition matrix, okay, is this. The proof is here, I will not go into the proof because it takes about 2-3 pages of notes, but it is a very interesting proof. Okay. Now, you know this is the transition matrix. You try to find out, basically R is a constant matrix, R is constant matrix. Okay. The whole purpose is finding out the transition matrix first. Okay. How R is related to the, I will tell you what R is related, that is at the end of the proof it will give you this. R is a constant matrix which is given by e to the power R t is phi t comma 0. Okay. E to the power capital R into t, one period. Okay. So, what is done is you start at 0, at the end of one period, what is the transition matrix? You evaluate, okay, because you are given the equation. All transition matrix have to satisfy what? This equation, right? Sorry, A t phi t comma is 0. They have to satisfy this equation always. You try to calculate this matrix by solving this differential equation. At the end of one period you calculate. Once you calculate, you know the relation. You find out the eigenvalues of this. Okay. This eigenvalue is related to this eigenvalue. Immediately you will know the eigenvalues of R, what is that, real and complex. If it is stable, you will say my system is stable. If it is not, my system is unstable. So, this is the procedure that is adopted to find out whether stability of the rotor blade in forward flight, not for simple flap problem, flap lag torsion stability. They use the Floquet theory, get the transition matrix and then roots of that theoretically. These are all done theoretical calculations. Industry, whether they use it, normally they do not bother. Okay, I will put it that way. Okay, because you try to design the system such that you do not get into any of these problems. Okay, this as a interesting result. You want to know what is the damping that is available, you want to know what is the frequency, what is that. Then academic side, yes, it is very, very important. But one of the equation, I wrote to you this equation, right. The problem, this is not just arbitrary problem, there are several examples for this. One of the example, because you are all structures people, one of the problem is this. I think it is a some beam with the, this is a buckling problem. Okay. You all know Euler buckling, static problem, but only thing is this tip load is time varying. If you write the equation for this in fundamental mode, because this is a continuous system, you have to do single mode. If you do, finally it will come to this form. Okay, it will come to this form in one mode. Each mode it will be the same equation. First mode, second mode, all modes will. Then they start looking at whether stability of this, for what values of lambda h they are related to these properties, and then P1 how they vary. Okay. Whether the system will be stable or unstable. Unstable means it will just vibrate and then break. Okay. So, if you go to Google search Matthew equation, they will give various places, but for structures from the point of view of vibration and aero field, this is the problem. Suppose I give you this problem, go and derive the equation. This is an axially loaded beam. Okay. If you want to derive, this is of course much easier, because I am putting same axial load throughout. I can vary the axial load. This you study if you take theory of vibration next time, okay. And the procedure is get the transition matrix, relate the eigenvalue. I am not going to the details because it is a little advanced to this, and stability of the system is purely based on the eigenvalue of this transition matrix, okay. Because composite materials for rotor blade, you always mention that it has a good, of course fatigue characteristic is good, damage tolerance is good, and you can tailor the properties. Tailor means you can create coupling, bending, torsion, coupling, anything by keeping the fiber, but you do not do any such thing in the manufacturing of an actual rotor blade, because you still do not know what all these coupling effects will really introduce to the blade dynamics. So, the composite material is used in such a way, the layup is that the final design will look like an isotropic blade, okay. So that I am safe, do not try to put too many things and then finally you really have no clue what is happening, because whether it is due to aeroelastic problems or whether it is due to this layup gayup. So, most of the times industry uses the material for something, but tailoring, even though it is said, but make sure that you do not get into any of these problems unless you are very thorough about what happens. Because one interesting point I read somewhere, they replaced the actual blade, metal blade. See, this is one of the projects. You say, I want to replace the metal blade by composite blade. You know the dimension, you know the mass distribution, you just make a composite blade. So, this is a major project. That means all my helicopters I will throw away old metal blades, now I will use composite blades. So, one of the project what they changed, what is that everything should be, you know dimension should be same, you know the mass distribution must be same, you want the stiffness also to be, distribution to be the same, but then only you will say dynamically they are same. And they made a blade, because dynamically means how many modes you will make its first mode, flap mode, lag mode, torsion mode. Few of them you say, okay, metal blade whatever it has, I will have the same thing in the composite blade. Design, it is not that easy design. You made the blade, put it on the helicopter, they fly, you find lot of vibration, okay. And this was in one of those articles, why, question mark, that is all, that is the end, because nobody knows what is going on. I say that everything is same, but I put this, I have more vibration. You follow what I am saying. So, there are many things which we do not know, and therefore, but you take the risk, but very calculated risk. That is why if you had listened to the talk what that visitor Viswanathan, Dr. Viswanathan mentioned, it is very important, but you try to learn more, but always cautious in your design, conservative thing, because you do not know several things.